Hello, everybody, and welcome to another episode of Data Analytics Computing. In this follow along, we will be going through the train test split and overfitting. As always, this series is mostly dedicated to just show how the code runs on Python and some basic statistical concepts. However, if you want a better treatment on both the actual Python code or the statistical parts of it, you should look in the description. Continuing with that, the train test split, here we are going to build onto the multiple linear regression video that I had a couple of weeks ago. You can find that in somewhere over here, and I recommend you to watch that video as we will be going through some Python concepts that we visited there that I will not repeat in this video. First, we need to import the required packages as always. We're going to use quite a bit of packages that we have used in the past, like pandas, numpy, pyplot, logistic regression, the train test split, confusion matrix, linear regression, and labeling model. We can just execute all of this and import them. After that, in this video, we will perform both regression and classification, although we're going to have a heavier emphasis in regression just because it's easier to show it. And we will fit multiple linear models. We will focus on the train test split or how to split the data. That will make more sense later on. This is a very important process to avoid overfitting. And I will also explain why it is important, an important program in machine learning. If you do not have the packages, you just need to run these commands over here in your console or in your command prompt to install them. We will look at the new data set, the loans data set that comes from Kaggle. And as always, you can always download it in the description of the video. I will always leave the link there for you, including with this code, so you can execute it on your own. I'm going to have two of them, one called loan 1, and the second one is going to be loan 2. Now, the trick here is that this data is already split, but we are going to merge it again. The pdconcat function allows us to just put it together pretty much. And this is better seen if we just take the head of this, loan 1. We take the head of loan 2. And we take the head of loan data. You can see here, this is exactly the same as the first one. Concatenate, the only thing that it did is put these two together. That's all that it did. And we can actually double check this. If we click here on loan 1, you can see how it has this column called status here. This is what it's in the testing data, in the training data, because we already know the status of the loan. If we go to loan 2, though, this is the testing data because there is no status here. And what happens with the second part of the dataset because it doesn't have status? If we scroll down, we can see it's null. All of these ones are coming from loan 2. So what concatenate this pretty much is just put together the two data sets by aligning the columns. And whenever there was no status here, it just fills up with nulls. But remember, the data is already split, and we are actually going to take advantage of that later. Now we will need to double check the records, and this is just confirming here. This is something called a Boolean value. It returns a Boolean that is true. Now, I won't go into detail about what is a Boolean value, but what this is doing is saying, is loan 1 the shape of it plus loan 2 the shape of it equal to the shape of loan data? And if we just execute this one, this is 981. And why did I put a 0 there? If I did not put a 0, I would have written this. I do not want this. I want only this part of it. I need this so I can compare it with the other two. And this is the number of records I have, 981. And guess what? Loan 2 and loan 1 shape. If we take this and we put it here, this is 614. And therefore, this needs to be 367. So it matches up perfectly. Now let's upset the data. We are not going to use all the variables that we have here. We are only going to use merit, education, applicant income, loan amount, credit history, and term. Loan amount is going to be a target for regression. And we're also going to use status for classification. However, because we only have status on the loan one data, we are not going to split it up with loan sub. We're going to split it up in a different way. Let's check for nulls first. As I already have said in previous videos, if we do this only, it's going to show us every single, and all of these are Boolean values. It just tells me if a value is null or not. You can see here, for this record, the credit history is null. If we use sum though, it's gonna tell me how many nulls there are over there. We need to drop the nulls because sklearn cannot handle the nulls. And we're going to use the drop NA method from here. And we're going to say x is equal to 0. That means it's going to look at every column. I'm going to drop that. And it's going to drop the entire record, not only that specific cell, if you think on Excel terms, but it's also going to drop the whole. So if you want to think about it, this one has a null here, record 11. It's going to drop the entire row, not only this. It's going to grow the entire row because all of this is related to this one. We're going to do that. And you can see that loan sub just shrank to 880 records. Now we will start with our linear models. The first one is going to be on the full data. We're going to use the full loan sub data with the applicant income. And we're also going to use all Y, all the loan amounts over there. You can see 680. We import the regression model from sklearn, the first instance of it, because we're going to be doing quite a bit of that today. And we're going to feed the model onto the whole data set. We are doing a simple linear regression in this case because of its simplicity and because we can show it in a plot. We get the score of the model. And you can see it's 0.26, that is not that bad. We are going to see later on why this is not actually true and it's actually overstated. We can get the prediction first. We need the predictions. And after that, we can start plotting. Now, it may seem that there's a lot coming on here, but you should be familiar with my form of plotting. And if you are not, review some of my previous videos. But these 4 lines are nothing more than for aesthetic purposes. It just gives it some formatting and some labels. Now, this is the most important part of it, though. These lines here, really quickly. This gives us the actual data. This gives us the actual predictions and how the line is going through the data. These two put the plot into 0, so it does not go into the negatives. And this just shows it. Now, if I plot all of these, go to plots, you can see it here. Why am I dividing in thousands? Well, because the numbers are too big and it will make this too difficult to plot over here. This is just better when I can just plot it and not have that many zeros. And that is why both the applicant income and the loan amount are in thousands. And I just divide it by 1,000 to make it that. Because if you review X, you can see how all the values are in actual dollars. And that is why I just divided over 1,000. And I just need to put into the plot, it is in thousands. Just remember to scale it back if you want to do some calculations. Now, here we can see how there is a lot of values here. There is a fair amount of values over here, and not that many that follow the regression line. And that is why it's only 0.25 accurate on that. Now, let's compare that with a train test split. This is the train test split that sklearn provides, and one of the simplest ones. It's an interesting syntax because first we take X and Y. We set test size is equal to 0.40. So this means that the test part of it, X test and Y test, are going to be 40% of the original data, and the rest is going to go into the trained ones. This one random state, you probably have seen it in my random forest video. It is just a parameter that allows me to have the same results. This split is random. If I run this 10 times, I will get 10 different results, but to make sure that you can check your results and see the same values and the same plots and the same models, I put a random state. And it could be any number. It could be 0, 1, 300, 1,000, whichever number I decided to be. After that, we're going to assign these values. This is going to generate me 4 values. The first one is X train, the second one is X test, the third one is Y train, and the fourth one is Y test. I could have called them anything else. It's just convention to call them in this way. We're going to execute this. And then we're going to generate a new instance of the linear model called linear model 1. We're going to feed that only on the train data. So check on here. In contrast with before, where we feed everything, all the data, we are only feeding this model. We are allowing the model to only see X and Y, only the train parts of it. We're going to do that. And actually, we can check that too. Let's check how big is X train. Now, it's pretty big. You can see it there. But that does not give us that much information, and we can just use our shape. It's 528. So it is not as big as the whole model that had the whole data. Now we score it on the test values. We score it on X test and Y test. Why? Because both X test and Y test are data that the model has not seen. I will explain this more into detail later, but think about it this way. We want to test the model on data that it has not seen before. The model already saw the trained data. The model already saw this because it was the data that was used to generate the model in the first place. We're going to go ahead and execute this. And see how the accuracy is this is way lower than before. This is just 14% pretty much. And we also predict on the test data to get our predictions. Now we're going to do the same plotting. It's exactly the same. The only difference here is that we're using X test, Y test, X test, and the predictions instead of the whole data. So we are plotting onto the test data only. That is way less, as a reminder, than the usual data. We can check how big X test and therefore Y test are going to be by just here in shape. It's 352. So it's going to have way less data points than this plot over here. And everything else is the same besides that. You can see here the big difference. This is the full data, and this is the test data. The test data has way less values than the full data. Interestingly enough, these 2 points over here that we considered outliers probably, and if we were doing a more rigorous study, we probably would like to actually filter some data here, stay into the testing data. And you can see here actually how the regression line looks different. And we're going to go more into detail about it later. But yes, these two models are not exactly the same. They are different. And that is one of the considerations with overfitting. Here, in the first one, we're feeding all the data. Here, we're feeding only the trained data. And then we're plotting this into the test data. Now, let's use the original partition. We're going to go back at lone 1 and lone 2 and just use a partition that was given to us by the author that generated the data. We're going to generate even one more regression model. check the grid shape here that is only used because our x is only 1. And then we are going to feed that into x2 and y2, that are our new variables based on the long one data, the training data. Remember that long one is the training data and long two is the testing data. We use the long two variables to make them the testing data. And first of all, we score them all. 20%. So it's a 21 around. That's a better value than our train test split randomly, but it is a lower value than the full model as well. Let's store the predictions. And now we can plot the results of this third model. Everything is the same, besides just changing the x test and y test for our new x2, x underscore 2 test, and x underscore y test. And the model is yet different. And notice this, how the data points are also different. This is because this partition is random. We did this partition without knowing anything about the data. This was a predefined partition already. And this is a full data. Therefore, you can see how it varies from model to model. And the regression line also looks pretty different if you look at it. Even so, this model here does not have any value that is more than 6,000, while this one and this one do have values more than 7,000 over here. Now we are going to just look at the actual models. And let's remember, a linear regression model is nothing more than a linear equation. It gives us an intercept and it gives us the coefficient. So we can just print that. Here, I'm just doing the same for the three models. I'm saying, give me the intercept of the model and the coefficient of the model and just plot it and print it over there. We're going to execute these lines. Here we can see how the models are actually different. The intercepts are different, not by a lot, but they are still different. And remember, the intercept will be where x is 0, the value of y. So in this case, could be interpreted as whenever you have a applicant income of 0, your loan amount should be this loan. That is rather high. And this is the coefficient. The coefficients are also different, if you notice here. And the coefficient will be interpreted as how much of a change there is on the loan amount given this increase on the applicant income. If the applicant income goes by $1, we can expect the loan amount to go by 6, 8, or almost $8, depending on which model you use. Now, again, you might be asking yourself, why are these models different? It is because they were trained on different data. This one was trained on the full data. So we have the regression line done on the whole data set here, as you can see. The second one was a random partition. And if you run 4 of these ones and we did not have the random state, or we had different random states, it will be fully different because we are getting different points of data over here. This third one used the actual data that was provided to us, the partitions that were provided to us. And it also has a different regression line and intercept. Now, why am I showing this to you in these 3 linear regression plots? Because linear regression is the simplest model. You can extrapolate this to any machine learning model, but basically the R-squared value that we identify here, the 25% here, it's overstated. These two, the 20% and the 14%, are way more realistic because we trained it in part of the data, but then we tested the model, we evaluated the model on data that the model had not seen. And this avoids overfitting because overfitting pretty much means, and it's not a big problem in linear regression because linear regression is just a line, but in more complex models, if you were to fit, for example, a random forest, support vector machine, or a quadratic linear discriminant analysis, that kind of stuff. Those models are highly sensitive to overfit. They can overfit on even one outlier over there. That is why we want to split the data. And the train test split is probably the most basic technique to do this, where we just split the data into two different data sets and then we test that. There are way more advanced methods to do this. But for now, I just want you to understand the reason why we do the train test split is because of that. We want to avoid overfitting. We want our model to not match perfectly the data because that will be bad. And in more complex models, it's a bigger issue. But we want the model to be able to predict and capture the trend. We don't want to capture random noise that may be around. We want it to capture the patterns, the general patterns that we have around. Now, how we train it again, it matters a lot. And the regression line is simple, but it still varies because it is based on all the points. The least squares algorithm is looking to minimize the distance with each of these points. And that is why you have it changing every single time that we are splitting the data differently. If we repeat this by multiple partitions and just feed the data into more and more of it eventually, we will get to a more robust approach called cross-validation that you also may know it as k-fold cross-validation, etc. Those are more sophisticated ways to evaluate the model and to get a better accuracy, more realistic accuracy, than you will get by just feeding the whole model. There are some models that do not require really the train test split because they have it basically programmed already in the definition. Random forest is one of them. You can use a out-of-bag score instead. That will give you a very realistic metric instead. But for most machine learning models, you probably should, and most predictive models, you should probably do at least the train test split so you do not overstate the predictive power of your algorithm. Now, we already said that these are random records all over around that are getting out in and out. This is even more important, again, with more complex models, and we will visit really quickly multiple linear regression. In this case, we are just going to go ahead and create a new model. And we're going to fit our X. So we're going to predict loan amount on the applicant income that we already did, the term of the loan, that is how long it was, and the credit history. We're going to take the Y, and we just call it YM and XM because multiple linear regression. And we're just going to go ahead and feed it into the whole. Now we're going to get our score. Now notice how our score is 0.26. We train this into the whole data. There is really no, even though I call this test and this M, there is no division here. So this 26% here is just to show you that the model increased its accuracy just because we added 2 more terms. But if we did a train test split again, this would probably be low. And we're going to do the same predictions that we did before. And just do our usual. And I'm not doing the train test split here just because of how complex the model will be, for lack of time to not make this video that long. But you could try to do the train test split here. It would not be that difficult to implement because you just need to take the XM and XY and rename some variables. You can see here, the model is way more complex. So it actually fits better the data to some degree. But because this is not the full picture of the model, you also have the credit history and the term. If you split the data, you're going to have even more variation than what we had in our simple linear regression models. just because of the fact that you're going to pick random samples of the data and you're excluding them from training. But it not only affects now one of the variables, but three of them at the same time. So keep that in mind. In more complex models, the overfitting problem is even worse because you may fit the noise over here. So for example, this might be the main pattern and this might be some other noise. If we took another data set of loans, we might not have a lot of this noise. Therefore, the best way to do it will be just getting more data or doing the train test split. And again, just reassuring, we train the model using the training data. That is why it's called training data. But we evaluate it on the testing data. We are using our model to predict data that it has not seen yet, because that is what we want. We want to actually see what the predictions will be on data that the model has not seen, because we already created the model from the training data. We do not care about the predictions on the training data. We already know them. That is why we had that Y train. That Y train was the observations that were interested on, and we saw them, and we trained the model of them, but we don't care about them because we already have them. We do not need to see them because we already have them. And all of them are shown here as the Y values. Now, we will take a very quick look onto logistic regression to see how it affects classification. We're going to take the logistic regression from a scale-learn and call it log model. We're going to take it, Y class is going to be our status. And we're going to put the order just because this ensures that the order is no and then yes. We're going to use labor encoder and then say transform that none and yes into 0 and 1. We can make sure if the classes are correct here, and they are correct. So again, what all of this did, this is a feature or a set scale. We just took the status column, no and yes, and just made them zeros and ones. 0 for no, Y for yes. And we actually can double check that on Y class. You can see here, now it's 0 and 1 instead of being no and yes. Now let's predict the data on all the observations, and this is the logistic regression model on the whole data. We will use the confusion matrix. You can see this model is horrible, but we are not going to bother on it because with this video is not focused on the actual model, but just to see how the train test split and overfitting affect our data. We store those probabilities here, and then we plot again. This is exactly the same. This is actually simpler than in linear regression because we just do scatter. We take x2, that is our data that we train on, divided by 1,000, and Y class. And then we also put this, again, the x2, that is our training data, and the log predictions probability. What is the probability that something is going to fall under those? And you can see here, we have here the logistic curve over here. And yeah, this model is pretty bad. If we actually look at it, this model is very bad on predicting values. However, you can see here how the model is feeding the data the best it can. As a reminder, if you have not seen my logistic regression video, there's going to also be somewhere over here. A value is classified as 1 if the probability is more than 0.5 and 0 if not. That is the cutoff value of the model for classification. Now we're going to go ahead and create a second model on what we're interested on, the train test split. We're going to create the Y class again and just repeat the labor encoder, even though we could probably use the Y class that we had before. And we are now splitting the data. We're doing exactly the same thing. We're just calling it X train 2, X test 2, Y train 2, and Y test 2. And we're calling this train test split, X2, Y class. The test size is still gonna be 40%, and the random state is going to be 350. Now we are training the logistic regression model into the data. And we are making sure again the classes are correct. We are storing the log predictions, but only from the test data. Keep that in mind. We are only taking from the test data. Getting the confusion matrix because we can. And see how the numbers are way lower than before because there is way less data over here. We take the probabilities. And now we do our final plot. Now, notice how not only the position of the logistic curve changed, but the shape of the curve also changed. Well, this is why logistic regression is a more complex model than linear regression. More so if we actually put multiple values into it and multiple features. We want to make sure that we're not overfitting the data because our model can change a lot depending on how we fit the data. We don't want to fit noise again. We want to get a model that can be generalized and we can apply to different data sets, not only to this specific data set that it was trained on. That is why we apply the train test split. And there are more elegant ways to do this, way stronger ways to do this too, based on more advanced statistics. But I really hope you understood the point about why we do the train test split is to avoid overfitting. We do not want to fit every single point, every single random variation, or some outlier that may be far away from everything else. Like in this example here in linear regression, these two will be outliers. Or in logistic regression, this one will be an outlier. We want to be able to see the data in a way that is going to help us predict other data that we have not seen. And with that, I will wrap up this video for today. I really hope you enjoyed it. As always, if you found this content useful, please subscribe, like the video, with a comment. It really helps me. And thank you very much. Have a good day.